Hey there. So, you've gotten pretty good at finding the highest and lowest points on a simple line in calculus. But what happens when we jump into 3 dimensions? Well, today we are building a solid game plan to find the absolute highest and lowest points on pretty much any surface. Let's get right into it. Think about it like this. Imagine I hand you a topographical map of a national park, and I ask you, where's the absolute highest peak and the lowest valley? What would you do? You'd probably scan the whole interior, right? Looking for mountains. But you'd also have to trace the entire border of the park because, hey, the highest point could be a cliff right on the edge. That exact intuition, that's the core of what we're doing today. So let's make a direct comparison. Back in single variable calculus, you had a simple process for an interval, right? You check for critical points inside the interval, and then you check the two endpoints. That's it. But now, in 3D, our domain is a whole area. So we still check for critical points on the inside, but instead of just two endpoints, we have to check the entire boundary curve. That's the crucial mental shift we're making. So here's how we're going to break this all down. We've kind of talked about this new dimension. Next up, we'll nail down our exact game plan. And then we're going to put it to the test with 3 classic shapes: a square, then a triangle, and finally a circle. Each one is going to show us something a little bit different.
Okay, let's lock in our game plan. It's really important to get not just how this method works, but also why we can even trust it in the first place.
So first up, the why. Well, we have this thing called the extreme value theorem, and it's basically our safety net. It promises us, it guarantees, that if our function is continuous and our region is closed and bounded, which we'll define in just a sec, then an absolute max and min have to exist. Our search isn't going to be a wild goose chase. So what do closed and bounded actually mean? Well, closed is simple. It just means the region includes its own boundary. Think of a fenced-in yard that includes the fence itself. It's why we use less than or equal to signs. And bounded just means the yard isn't infinitely large, it's contained. Our region has to be both for this to work.
And here is the how, our repeatable 3-step method. Step 1, find all the critical points inside the region. Step 2, find the extreme values on the boundary. This can be the tricky part. And step 3, you just list out all the candidate values you found and you pick the highest and the lowest from the list. That's the whole process right there.
All right, enough theory. Let's put this method to work. Our first example is a square region. This is a perfect place to start because its straight edges and nice, neat corners make the analysis pretty straightforward. So here's our first challenge. We need to find the absolute highest and lowest points of the function you see on the screen. And we're only looking at the space inside this simple square domain, where both x and y go from 0 to 2. Okay, step 1, check the inside. We take the gradient of our function, set it to 0, and that leads us to a single critical point at 1, 0. Now, here's a little catch. Notice this point isn't technically inside the square. It's right on the bottom edge, so it just automatically becomes part of our boundary check. Now, for the boundary itself, we have 4 edges and 4 corners. You could analyze each edge one by one, but for a simple shape like this, you'll find that all the important action happens either at that critical point we found or at the corners. And now for the final step. We just compare all our candidate values. That critical point on the edge gives us a value of -1, our lowest point. And when we check all 4 corners, we get a few different values, with the highest one being 4. So there you have it. Our absolute minimum is -1, and our absolute maximum is 4. Simple as that.
Okay, let's move on to our next example, a triangle. The new challenge here is that slanted boundary, the hypotenuse. This is going to require a pretty clever trick.
So our job this time is to find the maximum value of this really simple function, f of xy equals x times y. But we're restricted to this triangular region with vertices at 0, 0, 2, 0, and 0, 4. First, let's do the easy part. We check the interior. The gradient of xy is just yx. Setting that to 0, 0 gives us the critical point 0, 0. Well, that point is a vertex of our triangle, so it's on the boundary, and the value of our function there is, of course, 0. Now for the boundary. The 2 straight edges are super easy. Along the bottom edge, y is 0, so xy is 0. Along the left edge, x is 0, so xy is also 0. That means all the interesting stuff has to be happening on that slanted hypotenuse, the line connecting 2, 0 and 0, 4, which has the equation y equals -2x plus 4. So how in the world do we find the maximum value on just that line segment? Well, this is the really clever part. We can take the equation for that line, y equals negative 2x plus 4, and we can just substitute it directly into our original function. And boom, just like that, we've magically turned a complicated 3D boundary problem into a classic Calc 1 problem. Now we just have to find the maximum of this new single variable function. Let's call it g of x, on the interval where x goes from 0 to 2. And when you solve that Calc 1 problem, take the derivative, find the critical point, it tells you the maximum on that line happens at x equals 1. We plug that back into the line's equation to get the y value, which is 2. So the peak on our boundary is at the point 1, 2, where the function's value is 2. Since the value is 0 everywhere else we checked, 2 is our absolute maximum. Easy. All right, for our final example, we're going to tackle a curved boundary, a circular disk. Now, the big question is, can we still use that awesome substitution trick we just learned? Let's find out. Here's the setup. We need to find the absolute extrema of this function, 2x squared plus y squared, but only on the disk of radius 1 that's centered at the origin. Okay, let's run the playbook one last time. The inside check is quick. The only critical point is at the origin, 0, 0, and our function's value there is 0. Now for the boundary, the circle itself. And yes, we can absolutely use our substitution trick again. The equation of the circle lets us replace y squared in our original function. And once again, this turns our boundary problem into a much simpler single variable problem. And finally, we compare all of our candidates. We've got a value of 0 right at the center of the disk. Our analysis of the boundary showed that its lowest points have a value of 1 and its highest points have a value of 2. So we look at all three of our numbers, 0, 1, and 2. The absolute minimum is clearly 0, right at the center. And the absolute maximum is 2, which actually happens at 2 different points on the edge. So after all these examples, what is the one thing you absolutely need to remember? It all boils down to this 3-part mantra. Check the inside for critical points, check the entire boundary, using substitution if you need to, and finally, just compare all the results to find your answer. That's it. This method is incredibly powerful, but don't forget, it all depends on that guarantee from the extreme value theorem, which leads to a really fascinating question. What if your region isn't closed and bounded? What if it stretches off to infinity? Can you even be sure a max or min exists at all? That is a great question for another explainer. Thanks for joining me.